Okay, so today we are starting 13.7, which is, this is a very heavy, very dense section, all right? There's a lot in this. I've put up the solutions for homework for 13.6 as of yesterday. I've started to put up homework solutions for 13.7. If for any reason any of you came by my office this morning, I was not there from 9 to 11. I apologize about that. I had something come up. So let's start off 13.7, which is called surface integrals. All right, that's what this section's called, surface integrals. And what I thought I would do is summarize where we've been in terms of integration partially in this class. We've done double integrals, triple integrals, but if you look at all the integration that we've done where we have scalar functions, all right, where back in Cal 2, you did, you had a function, a scalar function, f of x, and it was defined on some interval AB, and we wanted to find the area underneath this, right? And so this was the formula for it. And the dx represented the infinitesimal width of a little rectangle that we were going to put in there, and then we're going to add them all up. That's what this was, right? Good? Then we learned that we can do these things called line integrals in this chapter, which is just a slight adaptation of this, where your curve, instead of your curve being a straight line segment on the xy plane, we can actually allow that curve to move around anywhere we want in the xy plane. And we define this line integral to be the integral over the curve C of the scalar function f of xy. Now it has two variables because you have to know the x and y coordinates at each point. And with respect to, anyone remember what that was? ds? Arc length, right? So this little ds was this little infinitesimal arc length that we got from here, right? And what we did to draw the curve is we came up with parametric equations, which we drew with the vector function, r of t. We put restrictions on t, and then this integral turned into this. So it's like the x gets replaced with the x function, the y got replaced with the y function, and then this right here, square root of the sum of the partial derivatives squared, right, is just the arc length. So this right here is just ds, right? Then what we did is we said, okay, what if this curve lives in three-dimensional space? So you have an x, y, and z coordinate for each point. Then we can do the same sort of line integral over a scalar function of three variables now. We still want to do it with respect to arc length, so that's a little arc length right there. We still come up with a vector curve that draws it, but it's three-dimensional instead of two-dimensional, right? 1, 2, 3 components for the vector. And then what we did is we tweaked the formula a little bit using vector notation. And this was just plugging in each of those component functions into the scalar function. And this right here was our d little s, right? Okay, today, here's what we're going to do. We're going to have a scalar function. I'm going to want to do an integral. I'm just going to put it right here. We're going to be doing a scalar function again of three variables. I want to integrate it, but this time the domain, which I should have said here, this curve is like the domain of our integration. This curve is the domain of our integration. Here, this line segment was the domain of our integration, right? This time, the domain of our integration, we want it to be a surface S in three-dimensional space, all right? So it's just this thing floating around in space. It could be, a sphere. It could be a paraboloid. It could be a lot of things. It could be a plane. But it's a three-dimensional surface, right? This is our domain of integration. If I want to integrate a scalar function on that domain, then it's actually going to become a double integral over S. Okay, this is the way we write it. With respect to, and this is the big difference today, instead of looking at a little infinitesimal piece of the curve, I need to look at a little infinitesimal piece of the surface. So that would be some little infinitesimal piece here, which I will call d capital S. And capital S here stands for surface area. So we were integrating here, this little d little s, that was with respect to arc length. Now we're integrating with respect to surface area. So we're taking like a little infinitesimal patch and finding its area. And that's this part, understand? So that's d capital S. And by definition, I'm going to put this on the board in a second, what this turns into is the double integral over d of f of something and then the cross product of the partials dA. So let me explain what this is. Let me just go ahead and put what's in here, r of uv. So what was r of uv from the last class and maybe the class before? What does a vector function of two variables draw? A surface, right? So what we're going to do is we're going to be plugging the points of the surface into our scalar function, right? That's what this means. This right here should be ds. And do you remember what the magnitude of the cross product of the partial derivatives of our vector surface represents? That times this? If you look at last class, we actually did a double integral over S of just that. Yes, what is this double integral right here? Just without that F thing in front. What is the double integral right there? That's the surface area of our surface, right? So that little piece in the back is our ds now, all right? So one way you could look at this is, do you remember this formula? Do you remember the formula double integral over d of 1 dA? Do you remember what that represents? The area of the region D, right? That's what that is. If I make this right here a 1, right? Or I should put it here. If I make this a 1, then this should just be the what? Surface area of the surface, right? If ds is this, then that becomes that formula. Do you see that? Now what we're doing is we're not allowing this to be a 1, we're allowing that to be a scalar function. Now we cannot visualize like what this is. It's not the area of a curtain like it was over there. Like over here, remember this was the area of a curtain. Over here we lost our ability to visualize it. And for here we definitely lose the ability also. Okay? You all right with this? All right, that's where we're headed today. We want to just do basic surface integrals. I'm going to put the formula up here from the notes. Given a scalar function f on a surface S with a vector equation given by r of uv with u and v and d, then here is the formula. So this is the surface integral, which turns into a double integral over d of this with respect to area. And d here, our restrictions are on u and v. All right, whatever our restrictions on u and v are going to become our limits of integration on this double integral. I think we'll just get right into an example. Find the surface integral over the surface S, x, y, z with respect to surface area of the part of the unit sphere above the cone z equals square root of x squared plus y squared. Pardon me?
Should we even try to draw it?
Yeah, I'm going to try and draw it. Let's see if we can. Yeah. Well, I have a unit sphere, right? My surface S is part of this unit sphere, right? So here's my unit sphere. But it's only the part of the unit sphere that is above this cone. z equals the square root of x squared plus y squared. Now you have to remember what that looks like when we studied these way back in chapter 10. I can get some points pretty quickly if I let x and y be 0, z is 0, right? So the origin there. And then what if y is 0? What if y is 0? This turns into z equals x, or the absolute value of x, right? Which would look like a v. So along one axis, or along one plane, when y is 0, you're looking at the xz plane. You should have a v, and then if you let x be 0, you should get the same thing, right? So it's going to look like there's your cone, right? Understand? So we're looking at where this cone punches out of the sphere. It should create this little cap up here, shouldn't it? And that right there is our S. Yeah? So what now? Yeah, we need to come up with, we actually need to find now some vector function, r of uv, that will draw just that cap for me. Not the whole sphere, just the cap. So how do you want to draw that cap? How would you draw the sphere if I asked you to draw the sphere? Okay, so you would use the spherical coordinates formulas, right? All right, so let's see. If we did the whole sphere, and let's use u and v. Let's not use what were we using before u and v? Theta and phi. Let's just go to u and v now. I've used two different formulas. I did one on my paper and one in class. So I want to stick with what we used last time. Did I say cosine u sine v, or did I say cosine v sine u? Cosine v sine u is what I used in class, right? Now, I actually have a 1 out here, right? Because it's a unit sphere. And then what? Sine v sine u. And the last one, 2? No. Just be... Cosine u. Okay. I want to make sure we're all... You all understand where that comes from? Okay. What are the restrictions that you put on v and on u to draw the whole sphere? Again, that's not what we want, but just so we're all on the same page, what would you put the restrictions as to draw the whole sphere? 0 pi for u, 0 2 pi for v. Now, if you remember, back from when we did spherical coordinates, this was like the phi, and this was like the theta, wasn't it? And do you remember how it works with spherical? You start at the origin, right? You're looking straight up the z-axis. Phi was this angle. Theta was your rotation this way, right? And rho was how far you go out. We know rho is 1. If I want to draw just this top cap, how much am I going to let phi move by? Well, whatever it takes to start here and swing down through there, right? I need to figure out what that angle is. What about theta? How far around do I want to go? All the way around, right? So I still want this to be between 0 and 2 pi, but I want my phi to be between, I'm saying phi, you understand you? I want that to be between that and something. Understand? So I need to figure out what this angle is. The angle, if you look at an angle straight up here, the angle that goes right there, that's u, right? That's my top restriction on u. So how would you recommend we do that? Okay, good. How about, yeah, we just draw a cross section. Isn't that a cross section, two-dimensional cross section right through the center of the sphere? Cut it open, look at it. That's what you would see. I'm trying to figure out what this angle is right here. I don't like calling it U because it's not really U. U is going to vary. Can I just call it like U tilde so it's something different? U tilde, is that all right? What do you know about any of this here? If I've cut it in half,
We know it's, each of those is 60.
how do you know it's 60?
So cutting it into 3 equal pieces.
How do you know it's 3 equal pieces?
Then we covered that when we're drawing the skull, the cone right there.
Because when you do the cone, you got absolute value of x for one day.
Yeah, okay, so look, when we cut it in half, think about it this way. I'm going to run out of the ability to show this.
Since that dotted line, which is isn't that bisecting?
Yes, it's cutting this in half, but I don't know what this is. I don't know if these are all equal,
Oh,
right? I don't know. Here, look, this is my three-dimensional, right? This is x, y, z. My sphere is in here, right? I've got my cone coming up out of it. If I decide to cut it right down here, right, and open it up, I'm really looking where x is what? 0. I'd like for us to just imagine then that this is the y-axis here, and this is the z-axis here, right? X is 0. If x is 0, what's the equation of this? If x is 0, that's the equation there is z equals the absolute value of y, right? That would draw this. Agreed? Y'all know why it's absolute value of y? Square root of y squared is the absolute value of y. I know a lot of times when we're doing algebra, we just say that that's y, but the only way that's ever true is if y was, well, y could be both positive and negative here. You get the same answer because you're squaring it. So we say absolute value, but okay. If that's z is the absolute value of y, then this part of the line is actually z equals y, and the other line is z equals negative y, correct? And z equals y means that this line goes out 1, up 1, right? Out 2, up 2, because the z and the y coordinates are the same. So the ratio here is the same. And I know that this distance is 1, don't I? That right there is 1. And I know that these two, whatever they are, have to be the same, which means it's a 45-degree angle, right? Agreed? This is 45, which means this must be 45 degrees also, right? So let's not use degrees, let's use radians. So 45 degrees is pi over 4. So I want my upper restriction to be pi over 4. Do you understand? Had they given you a different cone equation, you would have to go through this same process and try and figure out what that angle was. And it may not be so easy. You might actually have to determine, using like trig, sine, cosine, arctangent, maybe to get an angle.
Wouldn't it only be half of pi over 4?
What did I put? Pi over 4. Oh, yes. This is, sorry, this right here, just this. Hold on. No, hold on. No, this is pi over 4. Because look, this is 90 degrees, right? That's 90. So that's 45. That has to be 45. All right, we good? Questions? All we have done is come up with the R that draws the surface. That's it. Now what I need to do is remind myself what the formula is. This, I need to take F and evaluate it at the surface, and then I need to do this cross product partial derivative thingy, and then actually this is going to turn into D now because I'm actually going to go dA here. As soon as you put this in here, you convert it over to D. All right, do we know our restrictions for D? Like, Are we going to know these now? Yeah, we know what they are. How about we do some partials and crosses? Didn't we do that already last class? Did we do the partials and cross product of the unit sphere?
Yeah.
We did. Let's save ourselves a little bit of time. What do you get when what did we get when we did this? Anyone? I think we got sine V. Will you go look?
We got, yeah, we got.
Or was it sine, sorry, sine U. Sorry, I switched my U and my V on my work.
A squared.
Yes, A squared, but our sphere is, if you look at, you're looking at the other example. The one before that was a unit sphere. So we got sine U. If you go through the work, okay. So we're saving do you understand how much time we just saved ourselves, right? Okay. All right, so now we go and plug in to our scalar function the surface. So our scalar function is x times y times z, which means I'm going to take the x component of my surface times the y component of my surface times the z component of my surface. Then multiply that times this dA. So I have cosine v sine u, sine v sine u, cosine u, that's x, y, z, then sine u, then dA. And we can combine things together, right? Do I have any questions? Double integral. Let's see. Let's get all our u stuff together. Looks like I've got a sine cubed u, right? And a cosine u. That takes care of this, 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 and this. And then I have sine v cosine v or cosine v sine v. It doesn't matter how I do that, right? dA. You know, let's not do dA. Let's actually go to our limits. So we're going to have dv du or du dv. It's your choice. It doesn't matter because they're constants, right? Trapped between constants. So I'll do the v on the outer one, 0 to pi, 0 to pi over 4 here. And in that case, I've got to go du, then dv, right? And now at this point, I mean, we kind of know what we have to do, right? I'm also going to notice here that all my stuff with u's in it can be separated from all my stuff with v's, right? And when that happens, we can split this into two integrals and multiply those two answers together. So I'm just going to do it just to show off that we know what we're doing, right? We're going to be like, okay, I know this is just 0 to 2 pi. Let's see. That's my v's, right? So let me get all my v's in one integral. Sine v cosine v dv times, not plus, right? Integral 0 to pi over 4, and then all my u's. Sine cubed u cosine u du. Those should be pretty clean antiderivatives. Do you agree with that? This is a basic sub. Let u be sine v. Well, we shouldn't use u, but you let that be your substitution. The derivative of it's right there. So you should get, as an antiderivative here, 1/2 sine squared v, you're evaluating that 0 to 2 pi, times, I already know my answer is 0, right? What's sine of 2 pi? 0. 0, sine of 0, 0. This is all going to be 0, isn't it? It's going to 0 this out. But this one here, just again, we can just show that we know what we're doing. This is 1/4 sine to the 4th u, evaluated 0 to pi over 4. This one would not have given you a 0, right? You plug in pi over 4, figure it out. But since that first one zeroes out, I'm done. The answer is 0. Okay, so what does this answer represent? It is not the surface area of this surface. It's the surface integral. So here's the only way I can here's the only real way I can kind of get you to think of this. Imagine on that little cap that at each point on that cap it had a temperature. And the temperature was exactly the x-coordinate times the y-coordinate times the z-coordinate. Let's just say that's what it was. Then this integral represents like your net temperature. And the net temperature here would be 0. So there's some positive and some negative, and it's kind of wiping each other out, and you just get a net of 0. That make sense?
But only on the surface.
Only on that cap. Only on that little piece. And it could be, you could have anything up there. No, you couldn't do mass. That wouldn't work because you'd have to have negative densities up there. Magnetic field, well, we don't want, fields are different. That's the next part of this section, is what if we're on that cap inside a vector field? Then you have basically like some sort of what we call flux. All right, we have like a flow through this surface, and we're measuring that, and that's what the flux is. So that's the difference between having a field versus having a scalar function. A scalar function is more like temperature. Temperature at each a value at each point, right? Temperature is this at that point. Temperature is this at that point. A field would be, at this point, we have a vector in some direction with some length. And at this point, a vector in some direction with some length. That's the difference. Got it?
Got it.
Okay. All right, let's see what the next one is. All right, a couple of applications of this. By the way, I believe that's the only example I'm going to give of a surface integral. In the homework, I do a bunch of other ones, but that just gets you kind of going, all right? Oh, wait, no, I think I do one more. Someone can look at notes. I think I do one more, because we've got some special cases we have to look at. But here are some formulas. I'm not going to give you an example of these. I think you've noticed, hopefully you've noticed, that in one of the exams I gave you, you had to calculate center of mass in moments of inertia for a problem a couple of mini exams ago. It was real tedious. Then the last mini exam, I asked you to find the mass in the center of mass of a wire, which I never gave you a formula for. But the formula does exist in the book. For this, I'm going to give you the formula, all right? That's a big hint, that if you're having trouble with that wire mass problem, it's because the formula, you have to actually read the book a little bit, all right? So what if we have a sheet, right? A surface, not a sheet, but a surface, and we want to know its mass in center of mass? Then if we know its density function, so we know the density of the material at each point, then we can do a mass by doing the surface integral, right? So that's exactly like the F was, right? I'm looking at the density at each point, and I'm adding them all up, and I get my mass. And then to get x bar, we do this. To get y bar, we get this. And then to get z bar, we do this. So this is all just extending off of things we've done. And so really, what we have in summary for calculus, right? I always want to erase that. It's not ever going to come off. We can find the density of a flat region, a lamina is what we called it, even if the density of that lamina is non-uniform. And to do that, we use double integrals. We can find the center of mass of three-dimensional objects, right? Using triple integrals. We can find the center of mass of a wire, assuming that wire, we're assuming that the wire doesn't really have width to it, which is kind of weird, and we could argue about that. We can find the center of mass of that. And now we're saying if you have a three-dimensional surface, you can find the center of mass. And again, we could argue about that. How can you have a surface that doesn't have thickness to it? If it has thickness, then isn't it a solid? Isn't it? Three-dimensional solid? All right. But we can we can kind of get away with that if it's thin enough, I guess. All right, next. All right, we have a special case when we're doing surface integrals. In fact, there's 3 special cases. I'm only showing one here in the notes, but I'll write down the other special cases. And here's what it's saying. Let's say that your surface is actually easy to write. In other words, you can write it as a function of 2 variables. When we first started chapter 11, I believe, we were looking at functions of several variables. And we said if you have a function f of x, y equals z, then that draws a surface, right? And the domain was the ground. If our surface can be drawn like that, then the formula we have for surface integrals becomes a lot easier to do. Now, the sphere we just did could not be done using this special case because you cannot write the equation of a sphere as a function of just 2 variables. You have to draw it with the vector function. So we couldn't. Understand? So one example of something we could use for this is, let's say we wanted to do just like part of that cone. Remember that cone? What if I just wanted to do like part of it? I could use this as the surface, right? And not ever have to come up with r of uv at all, okay? If that's the case, then this is what the formula turns out to be. Our x, which used to be the u, is just going to be itself. The y will just stay y, and the z will be the function of x and y. So what we'll do is, remember how in the previous problem we took the scalar function and we plugged in the vector function into it? Right? This time we're going to take the scalar function and replace x with x, replace y with y, and replace the z with the actual function of the 2 variables, which would have been like that cone, just the square root of x squared plus y squared. But then the magnitude of the cross product, this, if you do the computation of this, will always turn out to be this. Okay, so let's just look at what this is. Magnitude square root, right? 1 plus partial of this function with respect to x, partial of this function with respect to y, square them both. And what this shortcut allows you to do is not have to compute the magnitude of the cross product of the derivatives, because it will always turn out to be this. Always.
We had one just like this in 13.6, right?
Where
Where we did it was the
Same exact thing.
yes, if you're trying to find the surface area,
Right.
yes, there's a simple formula if it can be written that way. Okay. Now, you can extend this idea where if you have the same situation happening, but this time, let's say x is some function of this time y and z. And I should point out, the reason why we use g here is because f is already being used as this scalar function f. That's why we're not writing this as f of xy. We don't want f to represent 2 different things in our problem. So we use g here. So what if instead of being able to write z as a function of x and y, we can write x as a function of y and z? How do you think this changes? This will be f of what? G of yz, y, z, square root, 1 plus. I'm just going to write, I'll do it in order. That's the same notation, isn't it? Partial g with respect to y plus partial g with respect to z squared dA. See how it changes? And then the last one, I won't write the formula down. I'll just say what it is. What if y is some function of x and z? We'll have what? F of x g of xz, z, square root, and then this partial becomes partial with respect to x, and that one becomes partial, well, it stays partial with respect to z. Understand? I'll give you two examples of those two cases. If you write x is equal to square root of y squared plus z squared, or you write y is equal to square root of x squared plus z squared, and let me put the first one up here. Z is equal to square root of x squared plus y squared. The difference between all those is just the direction in which the cone opens, right? This cone goes up like this. This cone comes out the x-axis at us, right? This one comes, what, out the y-axis like this? Right. X, like that. There's my x-axis. I think you understand. Do y'all see that? Okay. So if we have this scenario, we can use that formula, or this scenario, that formula, so on and so forth. I believe the next example I have here is going to allow us to practice with this. Can you all believe we only have two more class periods? Find the surface integral over the surface S of x with respect to the surface area, where S is the surface shown below. Okay, this is tied into why I gave you that handout and why we took some time on it, right? That's really big. Okay. I want to find the surface area, the surface integral over the entire surface, which means that we're going to need to do it one surface at a time. And you can look at this as, we're adding up the temperature along the outside of this object if it makes it easier for you to understand. So we want to find the total temperature on this side, total temperature on the outside, and total temperature on the back side, right? So what would you like to start with? There's three surfaces, right? We have, let's call this one S1, let's call this one S2, and let's call this one S3. That okay with you? All right. So what about oh, you want to start with S2? Okay. What about S2? It's in the YZ plane. Can you tell what its radius is? It's a circle, right? It's 1, and you know that because this right here, the green one, look at the equation of it right here, right? The radius is 1. So you know this has a radius of 1. The equation of that is x is 0, right? And now we have to really think about what we want to do. We can do this easy or we can do this hard. Here's the hard way. The hard way, and I won't work through the whole thing, the hard way would be to come up with my R of UV, which draws that, which we practiced, and we should all know how to do this. You want to help me? 0. V cosine u, V sine u, u's between 0, 2 pi, v's between 0 and 1. This will draw me circles with a changing radius. The radius is going to change from 0 to 1, so it should draw me that entire disk, right? Once I've got this, I can go to my formula. I can find the partials of this. Let's call this sub 2. I could find the partials of this. I could cross them, find the magnitude. I could do all that, right? And just plug things into the formula and go. But maybe this is a special case. Maybe it's a special case. Is that back part, that circle on the back side of this, is it is it z equals a function of x and y? So is it like a surface like this? Like, is it a surface up here like this? No, it's not a function of x and y. Is it a function of x and z, which means that you come out the y-axis? Is it a surface this way? No. Is it a function of y and z? Yes, it actually is. Your x value, right? Your x value, you could look at this as a function of y and z. It's actually g of yz, but what is the function? 0. It's 0, isn't it? Understand? Sure? If that's how simple it is, if that's our function, then what does our formula double integral over S2, because we're only talking S2, of f of x, y, z, magnitude, well, you know what, give me the short formula, the shortcut formula. It would be square root of 1 plus partial g with respect to y plus squared plus partial g with respect to z squared, right? That's what it would be. dA? dA, yes. I need to change one thing here. We're going to call this D2, all right? Because it's the domain that draws this surface, and change this to D2. It turns out that S2 and D2 are exactly the same here because it's flat, right? What is the partial of g with respect to y? 0. What's partial of g with respect to z? 0. So that's just what? Square root of 1? Which is just 1. Double integral over d2. Now I need to plug in to my scalar function, x, y, z. What is my scalar function? X, right? I need to plug in what? 0. Right? X is 0. You understand that? This right here is just x. So I replace x with whatever x is on this surface. What is x on this surface? 0. So this becomes 0 square root of times square root of 1 dA. And what's the double integral of 0? 0. All right? Now, I'd like, since this is our first surface and our first example of using the shortcut, I'd like to show what that would have been the long way, but I'm going to go quickly through it, okay? Can I show you the long way? All right, the long way I would have had to have taken this and taken partials. What's partial of R2 with respect to u? I know that's weird notation. So 0. Negative v sine u, v cosine u. What's the partial of R2 with respect to v? 0 cosine u, sine u. Cross these. Cross them. So here, what do we get? Negative v sine squared u minus v cosine squared u. I'll take care of that on the next step. Next part. What? 0, which 0, 0, so 0, and then where am I? Hold on. I did this one 0, 0. So 0 again. And what is that? Where? Oh, sine squared. Yes, thank you. Factor out a negative v, right? Pythagorean. So negative v, 0, 0. And now take its magnitude. And you get what? Square root of v squared, which is absolute value of v. But v is positive, right? So I don't need to worry about the absolute value. Okay, so that's the cross product, right? And what else do I need? What? I need to evaluate my scalar function on the vector curve. It's 0, right? Because it's x. So I come in here and I plug in 0 and I'm done. Now, I could have avoided all this by noticing that x was 0 and that was the scalar function. But I just want you to see what work it would have required instead of how quick it was with that shortcut. Okay, any questions? All right, let's now go and do S2. Or that was S2. You want to do S1? Okay, let's do S1. Why is that not wanting to come back here? Okay, which one was S1? The blue one? Okay, the blue one, S1. So how would you like to handle this? You want to go, R of uv, or can you look at that as being some function of two variables? Function of two variables, right? S1 is actually just x equals 1 minus z, which again is a function of y and z, isn't it? X is determined by y and z. Now, it turns out that our function doesn't need y in it, right? Y is not in there. But x is determined by z for sure. So I've got this. I've got double integral over, let's call this d1. Okay, d1 is going to be the domain that draws me this surface. Now I plug in what? The scalar function. I replace x with, well, x is this, right? So 1 minus z. And then square root 1 plus partial of g with respect to y. 0 squared plus partial of g with respect to z. -1, but then squared dA. Got it? Which is root 2. Take that out of the double integral. Root 2 double integral over d1 of 1 minus z dA. Now, this is a critical juncture we're at here. Does anyone have any questions on what I've done though thus far? D1 are the restrictions on my double integral that will allow me to draw that blue piece, right? 1 minus z is just the entire plane. Remember, this x equals 1 minus z is a plane, isn't it? I don't want to draw the whole plane. I only want to draw the part of the plane that's in blue. So how do I restrict my y's and my z's to draw just the blue part of that plane? Drum roll. -1 to 1 on both of them would draw me a square. So look at it this way. You've got that piece right here, and I'm kind of like transposing. My x-axis comes out like this. Here's my y, right? We're taking that and we're looking at its projection down onto the yz plane. That is a polar region on the ground, isn't it? I'm going to convert this integral to a polar integral, or cylindrical, however you want to look at it. Because I can't restrict y and z to make that nice. But if I go polar, I can. So I'm going to have my theta between where and where? 0 and 2 pi. And my radius should be between 0 and 1. Right? What are the substitutions I'm going to make? This is critical that you... Because if it's a normal polar region, we go x is r cosine theta, y is r sine theta, right? This time, we don't have x, right? It's y and z. So it'll be y is r cosine theta, z is r sine theta. Yes? And look at your integral here. It just has z in it. So I'm going to make this 1 minus r sine theta r dr d theta. I'm getting nods of approval, which is why I'm continuing here. Root 2 integral, now I'm going to change it 0 to 2 pi, 0 to 1, 1 minus r sine theta r dr d theta. Remembering that when we did this over here, we are going to let y be equal to r cosine theta, let z be equal to r sine theta, because our region projected down onto the yz plane is polar, and it's in the yz plane, not in the xy plane. And then you could distribute through, right? And integrate. Do we want to take it the whole way? No? You don't want to take it the whole way? Okay. So can I dot, dot, dot this? So we get that. We're not going to be able to get a final answer then. You're just going to have to do that on your own, all right? All right, that's S1. We still have S3. Now look at S3, which kind of looks like this. Not too bad. It's not so bad, right? S3? It's pretty good. Can you write S3 as a function of two variables? No. There's no way you can do it. You can't look at this as, anytime you can write it as a function of two variables, it's going to look like some surface that you go straight down onto a plane. It's going to be a nice shadow. Here, you can't, right? Because it wraps around itself. So you have no choice but to use the R of UV here. You've got no other option. Do you all understand? Okay, well, let's do it. I know you can do this. How are you going to draw that? I'm sorry? I didn't hear.
We did it last time.
We did something like this last class, right?
Yeah.
Or was it this exact one?
No, it wasn't this exact one. It's similar.
Okay, so look, if we look at it from this way, right, it's the green part. So it's just the edge, right? So I know I'm always going to be drawing circles in the, what plane? In the YZ plane, I'm drawing circles. It's just that the X is going to come out and go back in different places, right? So how do I draw a unit circle in the YZ plane? I've got to use these, right? So cosine, what do you want to use? U. Sine, U. That should draw me unit circle in the YZ plane. And then the V, right? The V here. And you'll control it in the inequality, right? So U is going to be between 0 and 2 pi to draw me circles. And then the V is going to be, well, what's the smallest V I can have here? V is my X value, right? So 0 all the way to the back. And then the front side, right? I want to go everywhere between here and here, right? Pick points. I'm going everywhere between here and here. And that's got to land on this plane, right? So what? 1 minus z. But z is sine u. There it is. I forgot to put v here. All right. Partials cross magnitude. Set up integral. Partials. Partial of R3 with respect to u, 0, negative sine u, cosine u. Partial of R3 with respect to v, 1, 0, 0. Ooh, beautiful. And cross them. Zero, negative cosine u. Hold on, I'm just writing down. It's positive? Definitely, okay. We're going to square it anyway, right? When we get the magnitude. All right, what's the last one? 0? Sine u. Sine u. Oh, wow, okay. Is that going to be 1? Magnitude? Root, what? Cosine squared u plus sine squared u? Yeah, well, what? Is it negative? Are y'all changing? Okay. Okay, and that's just 1, right?
Isn't it supposed to be 1 plus that?
Where? Root cosine squared. 1 plus. Not for magnitude. You're thinking of that shortcut thing. Yeah. No, we're just looking at the magnitude of the vectors, just square root of each of the components squared added together. All right, well, that's nice, right? That works out pretty good. So now let's set it all up. We have our double integral. We're going to be going over the region D, all right, D, which is the restrictions on u and v. We have x, right? Our scalar function is x. So I need to plug the surface equation. I need to replace the x with v, because that's the x component. So v. Then I need the magnitude of the cross product, which we know is a 1. Then dA, which is integral from 0 to 2 pi. I don't have a choice with the order here, right? 0 to 1 minus sine u of v d du, right? Dot, 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 or continue? Dot, 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 okay. Antiderivative 1/2 v squared, plug in, ooh. All right. Do you have the idea here? So when you're doing these surface integrals, you always want to look, can you do a shortcut? If you can, do it. If you can't, then you've got to do this. And then you would add up all those answers, yes. I didn't discuss it, I didn't put it in the notes, but if your surface, right, if you have some surface S that can be broken up into smaller pieces, right, S2, S3, if this is all S, then if you're going to do the surface integral over S, you can basically say that's equal to the surface integral over S1 plus surface integral over S2 over S3. Put them all together. Even if those surfaces come around each other and close in a solid, that's fine. All right, we're going to move on. So we're going to get into vector fields again. We need to establish a few things first. An oriented surface is a two-sided surface. And then I put in there just for fun, there are examples of one-sided surfaces. A surface with one side. Anyone ever heard of a surface with one side? Yeah? What is it?
Mobius strip.
A Mobius strip. We'll do a quick example. There we go. So this is a surface with two sides, right? And we're not going to argue that the edge here is a side, and this is. You could argue that there are what, like 6 sides to this? But let's just say one side, two side. Yes. So if you take this and you twist one end, keep the other one fixed, twist it, and then paste this together like this, you get what's called a Mobius strip. And if you look at this and look at my index finger and my thumb, they appear to be on 2 different sides of this. But if you follow the paper around, you'll come around back to your thumb, and then you keep going, and you'll come back to your index finger, and then you'll be back to your thumb. So my thumb and my index finger are on the same side of this. So it's a one-sided surface. Kind of interesting.
I feel like that's out there. You can't say that. How can you say that?
That's an example right there.
Obviously two-sided.
I think I would have to ask you to prove to me it's 2 sides. You won't be able to distinguish the 2 sides from each other. Yeah. There's an even more advanced problem where what you do is you take that same idea, right? Well, let me try this first. Imagine this sheet was kind of like stretchy. Okay, so what would happen if I take this side and paste it to this side, right? That would be a two-sided surface still, right? And what happens if I take this edge, this circle, and I stretch this thing around to this circle, and I make this circle be like the same as this circle. Stretch it around like that. Then what would I get? A donut, right? We call that a torus. Okay, so let me back this up. What would happen if I go twist this and put them together? I get this Mobius strip, right? But at the same time I do that, I got to back this up. Sorry, I'm going a little far away from class right now. Call this side A, B, C, and D. So when I do the torus, what I'm doing is A and C are becoming the same point. B and D are becoming the same points, right? And then I'm letting this edge go get wrapped around to this edge. Yes, that's your donut. When I do a torus, I switch these, right? So A is going to go to D and B is going to go to C. I want to do that, but at the same time, I want this edge and this edge to go to each other. Now, I can't do it, okay? I can't do it, but if you could, you get what's called a Klein bottle. And a Klein bottle is a 4-dimensional object, and it's an example of a volumeless container. It's a solid with no volume. Just like the Mobius strip is a surface with one side, it's a volumeless container. It's weird. This is all studied in a class called, if you're interested, if you ever have the opportunity, topology. Not topography, but topology. Usually you wouldn't see that unless you're a math major. But interesting stuff. I spent like a year studying the difference between a coffee cup and a donut. And at the end of it, there's really nothing. There's no difference, okay? But it begs the question, I mean, like, what is the difference between a coffee cup and a donut? I mean, we obviously you can eat one of them, right? You can eat one. You know, I mean, there's all these differences that we can say physical descriptions, right? But mathematically, what's the difference? And so then the question is, what do you mean by mathematically, right? And really what it comes down to is that they both, here's a donut, 3-dimension, that's not a very good donut. There's my donut, okay, you get it? And then here's my coffee cup. There's my coffee cup with my little handle on the edge. These are mathematically the same objects. There's no difference between the two. And the reason is if I draw arbitrary curves on this donut, that curve, I can shrink it down to one point without cutting through any part of the donut, right? That curve right there on the outside. But if I draw a curve that goes into the donut, comes back around the outside and goes like this, I can't shrink that down to one point without cutting the actual donut. And the same exact thing happens on here. I can draw curves out here that I can shrink down. I can even draw curves on the handle that I can shrink down. But there are some curves that I can draw around this handle, and then there's even the one around the cup itself, right? Which I cannot do it. So it's kind of like the piece of paper. You can deform it. You could deform a donut, or probably the other way around. You could, well, I don't know what makes more sense to you. I could turn this into this if I was allowed to deform them without cutting it or tearing it. Or I could deform this back into this if I'm allowed to like move things around. So they're mathematically equivalent. That's what topology gets into. I mean, in layman's terms, coffee cup and donut. Yes, yes. All right, oriented surfaces. See how that little, I should just take that out of my notes. That just wasted 5 minutes. An oriented surface is a two-sided surface in which the normal vector at every point on the surface exists, and such that the normal vector varies continuously over the surface. With surfaces like these, we can choose two possible orientations. So I think if you just look at this, there's a sphere, right? There's a sphere. We know that at every point on the sphere, there's a tangent plane, right? We did that last class. We have tangent planes at every point. If you have a tangent plane, you have two vectors. If you cross them, you get a normal, right? So at every point, there is a normal vector pointing off of this surface. As you move around the surface, those may change direction. They may get shorter, longer, but they vary continuously, which means they don't automatically, like all of a sudden go from here and then you move here and boom, and all of a sudden it's pointing inside. So that's what they mean by vary continuously. So we can look at all the normals pointing outward, which would be called positive orientation, or we could look at all the normals pointing inward. That would be negative orientation. But we can orient the surface, and any surface that we can do that on is called an oriented surface. All right? There are examples of surfaces which I won't get into that are not, you can't orient them. So how do we compute the normal vector of an oriented surface? Well, we've done this before. If the surface is given by a vector function, right? Then if we did the cross product of the partials, we did that on the sphere, cross product of those partials gave us a vector pointing out, which is what we use to find the equation of the plane. If we then divide that by its own length, it's a unit normal vector, isn't it? Yeah? If you take the negative of this vector, it's just going to point in the opposite direction. Okay? When your surface can be written as a function of two variables, x and y, so this is like a special case now, this cross product becomes this, and then the magnitude is this. So that should look familiar. This should look familiar to you. That's that was that shortcut formula we used a second ago? Square root of 1 plus partial of g with respect to x, partial of g with respect to y. Okay, but this right here, you would have to actually do the cross product to get that. With all that said, we now want to talk about a closed-oriented surface. So if the surface is closed so that it encloses a solid E, So imagine you have a surface that actually closes itself off. A sphere is a great example of a closed surface. The solid in which it encloses we call E. Then positive orientation of the surface is the orientation where the normal vectors point away from the solid. So back on that sphere, the reason why we called positive orientation was because this sphere encloses a ball, right, a solid ball. Positive orientation is where your normals point away from the solid. Negative orientation, they point in towards the solid. We good? All right, and we finally have gotten to a surface integral of a vector field over a surface. So now we're going to be looking at that surface that's been sitting there for the last 2 classes, and imagine that it's sitting inside of a vector field. That vector field might be magnetic, it might be gravity, it might be electric. I thought I said electric. I did? Magnetic, electric, okay. It could just be, some flowing material, whatever. But it's now a vector field. Instead of a scalar function, we have a vector field. We will define, well, if we're given a vector field on an oriented surface, S, with unit normal vector n. What's unit normal vector n? That was that cross product of the partials divided by its own length. And the vector equation of the surface, if we know it, then this integral, notice the formula here. It's a double integral over the surface S of the vector field dotted ds. So you're actually integrating with respect to, it's not surface area anymore. Do y'all see that? This is not d capital S anymore. It's d vector S. What the hell does vector S mean? I'd like to try and explain what it means in the formulas that you see here. Because this right here is the d capital S. I'd like to try and come up with some meaning for that for you. All right? Here's my best attempt at trying to explain what it is and what this whole thing called flux is. Okay, and I'm going to use an oriented surface. I'm going to use a sphere as an example. This is an infinitesimal little patch on the sphere, right? I'm going to move this thing. Come on. I got to get this over here. At every point on this sphere, we have 2 vectors that we're looking at right now. So the point I'm looking at is this point right here. Man, those look like they're exactly the same. Let me get to the different points so you can see that these are different. Okay, there we go. I think that's a little better. So at this point, I have a green vector at that point, and I have a red vector. What do you think the red vector is? That's your normal vector, okay? That's your normal vector. It's oriented positively, so it's pointing outside of the solid, right? What do you think the green vector is?
It's the vector of the field.
That's the vector field, vector. Right? So remember, when you're in a vector field, at every point there's a vector, right? Has nothing to do with the sphere, right? So there you've got, at that point, the vector field vector, and you've got the red vector, which is your normal. What we'd like to do is, actually, you know what? The black, I should have said the black vector is your normal. I apologize. The black is your normal. The red, get the hell over here. I'm trying to get you to see what the red one is. Can you tell from that what the red one is? It's a projection. Okay, so I have to go back because I said the red one wrong. At that point, we have a normal vector, all right? And we have a vector field vector. If I do the projection of this green one onto this black one, I get the red vector, right? And what that red vector represents is, let's go back to water flowing, all right? If you're looking at that point, the water wants to flow in that direction, doesn't it? With a certain magnitude, a certain speed. If I project it onto here, this red vector tells me what the flow is in that direction. And the length of it is shortened now, right? Because it's been projected. So the flow in that direction is actually shorter than the flow in that direction. But all I'm interested in is the flow out of the surface. So that red vector represents that flow at that point. Does that make sense? So let's go back and look at this red patch. And let's imagine that we take a bunch of points. That's 4 points in that patch, right? Those are all normal vectors. Let me give you some more of them. There's a couple more. Those are all little normal vectors in that little patch. Let me show you all the vector field vectors that go with all of those. Okay, so those are all the green vectors that go with all those black normals. Let me project all those green ones onto those black ones, each one of them individually. And I get these red vectors. And I'm going to now take the normals and the vector field out. Those red vectors show you the flow out of that patch in the direction away from the surface, right? Like these things are running perpendicular to the surface. So this is somehow measuring how much is coming out of that patch. If it's magnetic field, electric field, gravity, whatever it is, it's a measurement of that flow, right? And if I add them all up, and I get a bunch and a bunch and a bunch and a bunch, right? Then I want to know like a measurement of all of this, right? And that's what flux is. It is a measurement of all these vectors coming out. Now I'd like to go to the formula. I was trying to get us to see what this was, right? And I was saying that that was ds. So it's hard to, well, boy, you're really not going to be able to see it from here. Maybe you'll just have to trust me. Maybe next class I can put it up here for you. You have to go back to your projection formula. How do you project a vector onto another vector? There's a formula for it, right? If you come in here and you start putting your field with the normal vectors, things will start to cancel out, and this is what you're left with. So you have to believe that from this is actually your field projected onto your normal vectors. That's what that computation is. And then what you're doing is you're adding them up over the surface, if that makes sense. But when you project a vector onto a vector, don't you get a vector? Right? So this piece right here has to be a vector, which is why we say D capital S, vector S. All right, I hope that kind of makes sense. All right, let's try and see if we can do one of these. Find the flux of the vector field capital F of x, y, z equals y, z, x across the unit sphere. So they want flux, right? So here's what I want. Double integral over S of the vector field dotted with ds, which is double integral, and go back to the formula. I only pointed out one of the two formulas. The one I'm going to use mostly in here to begin this is this one right here, okay? We will use that one sometimes. So F dotted with R, partial of R with respect to U, cross partial of R with respect to V, dA, and this will be over D. Okay, R is the function that draws the surface. We've done this. This is a unit sphere, right? So what was R? Yeah, okay, let's go.
Sine U, cosine V.
Was it sine U cosine V?
Yeah. And then
Sine U sine V
cosine
cosine U.
and
Wait a minute. Is that right?
Yep.
V is between 0 to 2 pi. See, the thing is, if you're using phi and theta, it's hard to get mixed up. But if you use U and V, it doesn't matter what you use. So you can do the whole thing and switch them all and switch your limits, and it's the same answer. So everyone is okay with that? Yep. All right, we did earlier the cross product. We did the magnitude of it, but see, this time we don't need the magnitude. So what is the cross product of those two? Okay, hold on. It's a vector, right? Cosine U. Right here.
Yeah, in the same vector.
Okay.
And then sine V, sine squared U.
Sine V, sine squared U, and then
For the Z, it's cosine U, sine.
cosine U, sine U. Can I get a second on that? Anyone agree? Yes? Okay, good.
It was, I thought it was cosine of V sine squared U.
Oh, shit. Okay. See, this is where I knew we would run into a problem. Hold on. Cosine V sine.
And then it was sine squared sine.
I don't know.
Yeah, I think it is V.
Where?
Cosine? The-
Where? This one?
I think it's V.
Cosine V?
Yeah.
Okay. Is that good? Okay.
Looks good.
Yeah, that's it.
I hope that's good. All right, we're not going to work. We already did it. It's in your notes, right?
I mean, is that gonna be wrong if it was?
Yeah, it will be wrong if it's not right. But do you want to go through and do the partials and cross them to be double sure? Okay. It's more really like this is just a method. Like what are we doing, right? Like what's the method here? So what we need to do now is we need to get the field and dot it with that vector. Dot products are easy to do, right? But what do we mean by the field? Well, here's your field. I need to dot that with this. But see, that has y, z, and x. This has u's and v's. We need it all in terms of u and v. So just like we did before, everywhere we see x, we replace with this. Where we see y, we replace this. And where we see z, we replace this. So this double integral right here becomes double integral over d. What is my vector field? It's y, which is
Sine squared.
sine v sine squared u. I'm going to run out of room. Let me just do it over here. Double integral d sine v sine squared u. Okay. Now z cosine u. Oh, hold on. Oh, why didn't anyone catch that? Hold on. Yeesh. That would have been a disaster right there. This is x. This is y. This is z. All right. Sorry, the cross product was just for that second part, right? Okay. So this is sine. That would have been not fun after that, huh? Sine u cosine v is x. Shit. It must be too close to the end of the semester. What is this first component? Y, right? Which is sine u sine v. Then z. What's z? Cosine u. Then x. Sine u cosine v. I want to dot that with, I don't ever want to see that again. Goodbye. This right here. So cosine v sine squared u, sine v sine squared u, and cosine u sine u, if that's correct, dA. Now we can replace dA with du dv, dv du, and do our limits of integration because we know our restrictions on u and v, but I need to dot that, so I may as well dot it now. And I'll write my limits here. How about 0, 2 pi, 0 pi. All right, dot products. This times this. Sine cubed u, sine v, cosine v, plus this and this, sine squared u, cosine u, sine v, and then the last one plus sine squared u, cosine u, cosine v. D du dv. And then you get the pleasure of integrating that. If it doesn't clean up, does it at all clean up? Oh, these, are those two the same? Ah, they're so close.
Whoa, the last two ones, they're the same thing, I think?
Cosine and sine.
Oh,
V.
didn't see that. Shoot.
Yeah. That's life, man. Let's see if I have this one worked out. Give me just a second. Is unit sphere y, x, z. Yeah, I don't have this one worked out. The book, example 4 in the book, they work out a problem very similar to this, but they use the vector field z, y, x instead. And, you know, they get it to this point also. And once they get it here, they, you know, they don't show much work either. You know, you just kind of, but they show you what the answer is. You could do this now, right? I mean, given enough time, you could do that. I might go into three different integrals here. And in this first one, you know, split my u's and my v's into 2 integrals and multiply them. Then in this one, split my u's and my v's and multiply them. Then over here, split my u's and v's and multiply them. Then just put them all together. All right, let's look at what's next. We have some special cases when we do flux. All right. There's nothing that says that when you compute the flux of something that the surface has to be closed. All right? Your surface does not have to be closed. If it's closed, then the orientation is easy to figure out, right? Like if I have the sphere, positive orientation is outward. But if I just give you like a sheet floating here in space, what's positive orientation? Right? So that's what these shortcuts are for. If I have that situation, would you agree that I could say z is some function of x and y? Right? If this is the ground down here, right? X, y, z. You've got some surface up there. Okay, if we have that and our vector function has 3 components, p, q, and r, which, you know, in the last problem, it was like y, z, x or something like that. Whatever those are, we're calling p, q, and r. This will become this, which we already knew, except we're using x and y here instead of u and v. And When you do this cross product, you will get this. Now this is kind of like, you remember we had the shortcuts where we had magnitude of the cross product? And it was square root of 1 plus partials and all that. This is that cross product before you square it. So if you do the cross product of these two, here's the shortcut. And look at this shortcut actually does the dot product for you. So what it will be is negative p times partial g with respect to x minus q times partial g with respect to y plus r. These are in your sheets that I gave you, right? What page is that on of the sheets? Because this is a major thing to be able to reference.
Second to last sheet on that.
It's page 15?
Yeah. 14.
You have 14? Okay. Let me see what you have on here.
Yes, sir.
I only gave you one of those, huh?
Yeah, not all.
I didn't give you all of them. Okay, what I recommend you do is go to the notes I provided for this section online, because I have notes for all three special cases. All right? So it's this formula, and on the notes that I provide for you online, I know some of you I do not include this, so you might want to add this note in there. This is the formula, is if you're looking at your normals as pointing up out of the z-axis.
It's on
It is?
the, yeah, pointing up.
Okay, it's on the handout I give you. It's on the notes up there too?
Yeah, pointing, let's see,
Oh wow, I did update it. What the heck? Okay. Is that the CDF or is that the PDF? Okay, the PDF version does not have it. Yeah, the CDF is good. So if you're using the PDF, make sure you add this note to it. So let's just try and back up and try and figure out what this is saying. If we're trying to find the flux through a surface, and we're looking at the normal vectors as pointing upward, right? And our surface is a function of x and y, and normals are pointing upward. Then this is all we have to do. The double integral over the region D, which would be the shadow on the ground of this computation with respect to area, and we're done. Now, what happens if the normals that you have are pointing out the bottom, which will be the case sometimes? How do you think this formula changes? All the signs change. This becomes plus, plus, minus, and that's it. All right? Now, if we have a special case where our surface can be written as a function of y and z, so this time your surface is out here like this, you know, and your shadow is going to lie onto the yz plane. Understand? This is our domain on the ground. Then x is a function of y and z. Then you don't have to go through all this mess of coming up with the formulas and crossing them. This is it right here. As long as you treat the normals as the ones pointed out towards you, okay, like out towards us. If you want to make your normals go into the page or towards the negative direction of the x-axis, then these will all change again. Negative, plus, plus. All right? And then finally, if your surface can be expressed as y equals a function of x and z, that's like this. Here's my surface this way. Then normals, which way? Out the right. Here's the formula. Is that what I have on my CDF? Out the right. I think on the PDF, I don't say anything. And it's opposite on the PDF, isn't it? On the PDF version, doesn't say positive, negative, positive?
Yeah.
Yes? Okay, so if you're going to stick with the PDF version, that's your normals pointing out the left. This is what you have when the normals point out the right. Does this make sense or not? Use this formula right here if you want your normals pointing this way. If you want the normals to point out the left, switch the signs. That's what's in the PDF. I have 6 minutes. I think I have enough time to do one. At least set it up. Find the flux of the vector field. There's your vector field. This is The surface is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above this region. So it's giving me this paraboloid. Okay, its region, if we look at it straight down, the region on the ground, right, is a rectangle. And that is a function of x and y, isn't it? So this is g of xy. This is p, what? Q, r, right there, right? And since it is a function of x and y, I can use a shortcut. It's telling me to use upward orientation for the normal vectors. So I want to imagine my normals are coming up here. So that means I can use the formula directly the way it appeared in the notes, which is this first one, right? I'm going to do double integral over d of negative p. Yeah, if the normals are pointing upward out the z-axis, right, upward, times partial g with respect to x minus q times partial g with respect to y plus r dA, which will be equal to double integral over d. What's negative p? Negative p. Negative xy times partial of g with respect to x. What's the partial of, I'm sorry, I'm a little off here. Here's my g. What's my partial of g with respect to x? What's that? Negative 2x. Okay. Now, negative q, what's negative q? Negative yz times partial of g with respect to y, negative 2y, and then plus r, plus zx. Got it? dA. Now, my region D on the ground is given to me by this restriction. So I knew that on the ground, x, y, I was inside this box, right? That's D. So I'm going to have d what over here? dx, dy, or dy, dx. It won't matter, right?
Do we plug in 4 minus x squared minus y squared?
Yeah, okay, so look, what we have to look at now is if I'm going to be integrating with respect to x and y, I need all these to be x's and y's in here, right? I have a z in here, but z is 4 minus x squared minus y squared, and that z right there is 4 minus x squared minus y squared. So I'm almost done setting it up. Integral 0 to 1, 0 to 1 of negative xy. I can actually put those together. What's that? 2x squared y. This one plus 2y squared z, but z is 4 minus x squared minus y squared. And then last one plus x times 4 minus x squared minus y squared. dy dx. There it is.
It's gonna happen.
This turns out to be 713 over 180. You would just distribute all this out, right? Multiply it all out, and then it's just pretty simple integration at that point. All right, so there's some more examples, of course, that I want to do. I'm not going to have time. I've got that one and that one. Now, just so you know, these two problems, example 5 and example 6, are actually out of your homework. They are problems where'd it go? 27 and 31, I believe. No, 27, 31. Yeah, I think that's 27 and 31. Here's what I'd like for you to do for homework for this. I pretty much have presented all the ideas. I haven't done enough examples yet. I will do these 2 examples when we start class next time. But I'm asking for homework that you look at problems 5 through 31, odds. And this is off of page 817. Now that's a lot of problems right there. So if you want, what you can do is at least just get them set up, not grind out all the answers for them, and then go back later and try and get like the numerical result. Like just get to the integral. All right, and if you want to know if you got it right or set it up right, you can let me know. But if you get hung up, just realize I'm going to do a couple of more examples. See, we have some examples where we have to do flux on an object like this, where you've got 2 surfaces. So like if you look at this surface right here, you have some normals pointing this way and some normals pointing that way, and you have to adjust your formula for that. So I'd like for you to see me do that before you try it, but it's well within the ability of some of you in here to do that, to try it. So, all right, next class, finish it up. 2 sections left.